So in this video, I'll be talking about the full concept of hybridization, right? Like what it is, what does it actually mean, and how we'll be finding it, right? So what does hybridization mean? Like in my previous video, I discussed that how it arose, like what was the need of hybridization and how the VBT got rejected, right? If you haven't watched that video, you can go back and watch my previous video first and then come back again, right? So hybridization, what basically hybridization is a process, right? It is a process in which atomic orbitals of same energy or nearly same energy combine to form same energy orbitals, right? Now what does that mean? It means that atomic orbitals of same energy, like they can be, for example, I'm having this is S and this is P, right? Right, this is P. So basically here this is P. These can combine together or these can combine. The orbitals of same energy, like you can see, they both are having not same energy. This is S, they don't have same energy, but these are degenerate orbitals. The P1 is having the same energy but not S1, but they are having a nearly same energy, right? They're having nearly same energy, right? They are having nearly same energy. It means they can combine together, right, and to form a same energy orbital. So like in my previous video I talked about that there's the same bond length, same energy, so they will form same bond length and same bond energy in the molecule. So now let's understand this by the help of CH4, right? CH4, the example which I took to explain you VBT, right? So we know that atomic orbital of the atomic number of carbon is 6, right? Let's find out the configuration. 1s2, 2s2, 2p2. Now let's make the orbitals of these. Right? This is like this, and this is like this is like this, and this is empty, right? Now what will happen, it will not go in the, like first of all there is a valency 2 and it has to form the bonds which like it has to form 4 bonds, right? So it will first go in the first excited state, right? What will happen, this electron from here will jump to here in order to give the valency of 4, in order to give the valency 4. Now what will happen, now this will, right? Now you can see this is a S orbital and this is a P orbital. They have having nearly same energy. They will combine together. And they will form 4 orbitals. and they will be known as sp3, 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 sp3. Now, like we combine together, we combine one s with 3p, right? There were 3p basically. We can't write this. Basically, there were 3p and there was only one s. Obviously, one s and 3p. We write this like this. Now, they all have same energy, right? It means now the bond will formed, the bond will be having same bond length, same energy, right? Now this is known as sp3. You know what, this sp3 contains the characteristics of its parent orbitals. Now what are parent orbitals? Parent orbitals are these, s and p. It will be more having the character of p, more character will be, because p is greater than the s, right? More character, and there will be the less character of s, right? The character of s will be less over here, because you can see there's only one s and there are 3p, so obviously there will be the difference. Okay, another thing which should be note over here, that the number of orbitals, the number of orbitals combined is equal to number of hybrid orbitals. Now what does that mean? You can see over here how many how many orbitals were combined over here? 4, right? And how many, now after combination, how many are formed? 4, right? So it means the number of orbitals combined together will be equal to number of hybrid orbitals. Now you'll be wondering that what does hybrid mean? Hybrid, actually these are hybrid. Hybrid means or and something which has been changed, right? So they have been changed, like previously there was something else, now there's something else, like, so they are known as hybrid orbitals. So now let us understand the methane, how we'll be forming methane. We know that now this sp3 is formed, right? Okay, can I move this over here from this, right? Okay, now let us find the configuration of hydrogen, right? There are 4 hydrogen basically, and we know the configuration of hydrogen is 1s1, right? So it will be like this. Now it will be like this, this and this. Now it will form bond with this 1sp3, this one sp3, this one sp3, and this one sp3 over here. So by, like, let's make the structure over here of methane. This is carbon, this is hydrogen, 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 right? Now you know that there is always s sigma bond, or like the s orbital of s, because it's having only one electron which will be placed in the s, so it will use obviously s, s, s and s, right? But it will be, now this will be using sp3, sp3, sp3 and sp3, right? So it means they are same orbitals, s combines with sp3. You can say that now what is happening, s is combining with sp3. There's only one type of bond, so obviously there will be same energy, same energy, same bond length, and same extent of overlapping too, right? So you can easily understand that why there is same energy and why there is same bond length. Okay, Basically, the structure of methane is not like this. It's something else. Like having the geometry of tetrahedron. Okay, now these sp3 orbitals, arrange themselves, or you can say they can arrange themselves, or you can basically they will orientate in such position that there is low repulsion. Obviously they are sp3, like they have same energy, but obviously they are containing electrons, so there will be repulsion. So they will arrange themselves in a that way that there will be low repulsion. Why there will be low repulsion? In order to increase stability. And because of this, character, hybridization gave the concept, like hybridization is responsible for geometry. It is responsible for geometry. The hybridization is responsible for geometry, right? So I mainly have completed all the points, but still I'll be forming the whole list of tables. Okay, now let's discuss the basic structure of methane, right? Okay, before moving that, I should tell you that I've almost completed all rules over here. That there is a shape of hybrid orbital. Like we know that the shape of S is spherical like this, so shape of P is like this, and D is like if you haven't gone through these shapes, please do watch my YouTube video in order to clear your concepts, right? So this is the shape of D, double dumbbell. So now what's the shape of the hybrid orbitals? They are like this. Let me make them. This was a smaller loop, and there is a large loop. Okay, this is known as small lobe. This is the small lobe, and this is the large one. This is the large one lobe. So basically, we don't actually, sometimes we, or mainly you can see it in some textbooks, or in some, we don't represent this. We only represent the larger one. We don't represent this, right? We don't represent this small lobe. So now let us discuss the basic structure of methane, right? Here I am having carbon. Now one hydrogen over here, one over here, one over here, and one over here, and now it will form bond like this, right? Hope line is clear. Right, and now it will form the hybrid orbital, like we have combined this with sp3, right? Now it will form the hybrid orbitals. How it will be forming? It will be like this, right? This will be like this, or you can, so here the geometry is tetrahedral. We won't be saying shape tetrahedral, and the bond angle between them will be 109.28. This will be the bond angle between them, but I will be discussing this bond angle and the geometries and the types of hybridization, right? So I hope this concept is clear to you now. that how it is forming. Let me show you the geometry of, right? You can see over here now. Maybe it's clear to you. Now you can see over here, this is a carbon, right? This is the carbon atom. This is first hydrogen, second one hydrogen, this one fourth hydrogen, third and fourth, and it is forming a tetrahedron, and the angle between this, right, is 109.28. The angle is 109.28. So I have covered basically all the rules. Okay, there is another rule that in hybridization, basically which kind of orbitals will participate, right? So half filled, fully filled, or empty, they all can participate in hybridization. They all can participate in hybridization. Now the concept of hybridization, is for only, it's for only sigma bond and for the lone pairs. It is for the lone pairs. The concept is not for the pi bond, right? The concept is not for the pi bond. It is only for the sigma bond. It is only for the sigma bond, and it is only for the lone pairs. There is another thing, that the hybrid orbitals orientate such that repulsion between them is minimal. I have talked about this over here. Yeah, there, that they orientate in such position, not sp3 only, it can be any, hybrid orbital can orientate in such position that there is a low repulsion in order to increase the stability, and this gives rise to the geometry, basically, right? So this is giving the rise to geometry, right? So now we will be discussing about, okay, the hybrid orbitals. The hybrid orbitals are named after the parent orbitals. Now what does that mean? For example, if we are having their here s, and which will plus p, so now they will known as sp. If you are having s plus 2p, now they will known as sp2 will be there, right? If I'm having like s plus 3p, then there will be sp3. Or if I'm having s plus 3p plus 1d, then it will be known as sp3d. Or if I'm having s plus 3p plus 2d, now it will be known as sp3d2. It will be known as this, and here 6 orbitals will be forming. 6 orbitals will be there, because count 2, 3, 4, 5, 6, and here 5 orbitals will be there. Here only 4 orbitals will be there. So now how they are named? They are named after the parent. So what is parent over here? These both are parent. This is parent, this is parent. So I hope the concept of hybridization is clear to you. What was the need of hybridization, the rules? I have tried to cover all the rules, right? And now in the next video I'll be talking about the types of hybrid.